Hi, now welcome to the run through for Unit 8. Let's go through each bit in turn. So to start with, here is a plan, scale plan of Julie's bedroom, where you can see here the scale, 1 foot square, is basically one of these little squares. So every square is worth a foot. And you can see you've got a chest of drawers, you've got a door, you've got the doors to a wardrobe on the wall. Julie's bed is 6 feet long and 3 feet wide. Draw her bed to scale to fit in the corner along the wall opposite the wardrobe. Okay, the wall opposite the wardrobe is this one. Okay, so here's the wardrobe opposite here, and we want it in the corner. It can't be in this corner because there's already a chest of drawers. So we know that the bed needs to be 6 feet long and 3 feet wide. You need to decide if it's going to go this way, so 6 down, 3 across, or if it's going to go 3 across, 3 down, 3, and then 6 across. The only way it's going to fit is that latter one. Because if you go 3 this way and then 6 down, you'll find that you're actually touching the wardrobe, which doesn't fit. Because there's only 5 squares between the wall and the wardrobe. So it has to be 3 across this way, going the 6, 1, 2, 3, 4, 5, 6 bits across, and then it's 3 away from the wall there. That would be the perfect shape. So you can shade that in if you want, or you might want to draw just right the word bed, I don't know. But that's what you need to have for this one. And then in part B it says, will the wardrobe open? Give a reason for your answer. Well, the wardrobe doors. So these are the 3 wardrobe doors. You can see that each of those wardrobe doors is 2 feet long. They're 2 of the squares. Now, in order for them to open, we need to have at least 2 feet as the distance from the door up to the next obstacle, which would be the bed. The only one that could be tricky is having this door and this door open at the same time, by the looks of it. If you open this door here and get it to as far open as it will go, it'll be 2 feet long. It'll get to about here. It's not even going to quite reach the bed. The same here. Here, there's no problem apart from this door. So actually, yes, the doors will open. So our wording, what we need to put here, is that yes, they will open, because there is at least 2 feet from the wardrobe to the bed. And then maybe an opening note, and the doors are all 2 feet wide. Something like that. Okay, words to that effect will get you the marks there. Next up, complete these equivalents. There is an error on the original copy of this, which I have corrected here, but hopefully those of you do this for the first time this video is used, that we told you that that is not kilometers, it's meters. So, a scale. 1 to 40,000 is the equivalent of 1 centimeter to a certain number of meters. Remember that when you've got a scale that's not given with any units, it is the same unit for both. So this could be 1 centimeter on this side is the same as 40,000 centimeters. So now the question is, if 1 centimeter is given as 40,000 centimeters in a scale, then I can change this second one to meters as required here, because that's still 1 centimeter, which I've got. What's 40,000 centimeters in meters? You need to divide by 100. It's 400 meters that you're left with. Okay? 40,000 centimeters is 400 meters, just by dividing by 100 there. This next one, 1 meter to 5 kilometers, is the equivalent of 1 meter to something in meters. Well, again, the 1 meter this time is the same. So what I actually just need to do is change that 5 kilometers so that it's in meters. And it would be the same as 5,000, because we know that if we multiply the number of kilometers we've got by 1,000, it will tell me how many meters it is. Next up, the more tricky one. 2 to 350 is the equivalent of 1 millimeter to a certain number of centimeters. Well, to start with, this is the same as having 2 millimeters. Let's try and rewrite that, because we'll keep the units as what we want them to have at the end. 2 millimeters to 350 millimeters. Well, that means that I could have 1 millimeter by dividing by 2. That means that the 350 is going to change to 175, just by dividing both sides by 2. So now I need to change this, because now I've got millimeters and millimeters, but I want this one to be centimeters. So to go from millimeters to centimeters, what I need to do is I need to divide by 10 because there are 10 millimeters in 1 centimeter. Therefore, dividing by 10 gets me 17.5. So I've got 17.5 centimeters is 1 millimeter for that scale. Next up, we've got here a map of an island. You've got to calculate the real distance between Axford and Bayton. Axford and Bayton are these 2 points here. Now, this is going to be tricky to do on the screen because actually what you need to do is you need to use either a ruler, but I can show you how to do it using the grids. So what we can see straight away is the scale. Every square is worth 5 kilometers. Now, if you were using this on your paper, you might use your ruler and realize that every one of these squares is half a centimeter. It won't be on the screen, but it is on your page. So that would mean that you could literally just get your ruler and line up these 2 points. You'll see that it's 5 centimeters wide. And then using your scale, if every half centimeter is 5 kilometers, every 1 centimeter would be worth 10 kilometers. You just do your 5 centimeters times 10, you've got 50. But another way to do it is to consider the triangle that we can actually make. If I go from Axford up to Bayton, you can see that I can form a right angle triangle, and this avoids any issues with the scale. So here I've got a nice right angle triangle. That right angle triangle, you can see in terms of squares across, I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 squares. Well, if every square is worth 5, I've got 8 times 5 there, so I've got 40 kilometers going across. And likewise going up, I've got 1, 2, 3, 4, 5, 6 squares. Well, 6 times by 5, I've got 30 kilometers. And then using a bit of Pythagoras' theorem, I can work out that direct length there. We know how to work out the length of a hypotenuse. We just use by Pythagoras. We're going to have this time a squared plus b squared is equal to h squared, where our a can be 40 plus 30 is equal to h squared. 40 squared is 1,600. 30 squared is 900. Adding them together, you'll get 2,500. And if you take the square root of that, you will get h is equal to 50, and the units were kilometers. So that's the same again. Okay, so not more than one way to get it. You could have done it using your ruler, but you can also do it this way. Okay, next up it says, for part B, find the approximate compass direction from Axford to Calcott. So from Axford to Calcott, you can see that that's going this way. Okay, so what I want to do is include maybe a line that goes from these 2 bits. When they say the compass direction, what they mean is north, south, east, west, northwest, northeast, southwest, southeast. It's one of those. Now, if I was thinking about a compass direction, where this was my north line, you can see the distance I've moved. I've got about 45 degrees anti-clockwise. That is the exact same as going northwest. Okay? Just as a little reminder, in case anybody has forgotten the compass directions, if this is a compass needle, this is what it would look like. We've got, first of all, north going up, south, east, west. I remember this as an old saying, never eat shredded wheat. Shredded wheat is a British cereal that we have for breakfast, but never eat shredded wheat. And then the bits in between, so between north and east, you've got northeast. Between east and south, you've got southeast. We always use south or north first. Between south and west, southwest, and between west and north, northwest. So that's how we get these setups. Okay. So knowing that, you can see from the diagram, this is approximately going northwest. So we can say north west. Now, if you wrote NW, I guess you would get the marks, but it's good to write the full wording for the answer. Okay, next up. It says, a microlight travels from Bayton to the pines. Determine the three-figure bearing on which it should fly. Okay, so for this, we're going to go from Baton, which is here, to the pines, which is here. I'm going to remove these bits so that it doesn't look too confusing. Okay, so first of all, I need to put my line in, my line of direction. So the pines connects to Baton like this. To work out the bearing, now the important thing is where we're taking the bearing from. It says from Baton. That means that we are taking the bearing at Baton. So when I draw my north line here, what I'm looking to do is work out the angle that is made between north and the direction that points to our direction, to our destination. I'm just going to alter it slightly because it wasn't too accurate. That's a bit better. Okay? So I want to work out this angle here. Now, there's two ways you could do it. You're obviously going to have to use a protractor. So I'm going to get a protractor out here. One thing you could notice straight away is that if I turn it this way, that I've automatically got 180 degrees covered up until this point. So all I really need to do is work out the angle from this point onwards, and then just add that on to 180. You'll see that according to my diagram, which is a little bit off actually, there we go. It's because the T isn't on the right point, and that's a little bit askew still. Just speeding it up a little bit. There we go. You can see we're more or less at 11 or 10 degrees there. Okay, on your diagram, because you will have done it with a pencil, it's nice and neat, it will have looked a bit more accurate. Try and match these up a bit better. There we go. It should be about 10 degrees extra. Now, knowing that I've done a full 180 to here, I need an extra 10 degrees. 180 plus 10, I've got 190 degrees. So that should be on a bearing of 190 degrees. Now, if you have one of the protractors that looks like this, all you would need to have done is put your 0 point here and then counted along to 190, and that would have worked as well. But most of you have the 180 degree calculators, but if you've got a 361, you can do it that way as well. It's the same logic. Okay, and you can see actually that on my 361, you can see 190 there. Okay, so we've got that one now. And then the last one, an aeroplane P is traveling on a bearing of, an airplane is on a bearing of 110 degrees from the radar station at Calcott. Well, let's note that down. 110 degrees from Calcott. So let's go to Calcott. Let's get rid of these bits first of all. So from Calcott, which is over these ways, I can put in my north line, which is try and get as accurate as I can. There we go. So this Calcott, I want to get a bearing this time of 110 degrees. So I'm going to put my protractor on the needle point for Calcott, and I'm going to measure round to 110 degrees. So I'm going round to here. That's the point I'm after. What I'm going to do at this stage is I'm going to draw in a line connecting those 2 points. I'm going to make it faint though, so I'm only going to go over lightly so that you can tell that it's not the final answer. It's just part of the answer. So I've got this line connecting up to here, and it goes through that point. Next up, the information that the text gives us is that it's also on a bearing of 215 degrees from the airport at Baton. So from Baton this time, I've left in my north line from before, I now need a bearing of 215 degrees. Again, there's going to be 2 options for you to work that out. You could notice that there's 180 all the way round to this point. So what do I need to add on to 180 to get 215? Well, for that, I'm going to need to add on 215, take away 180, which is 35. So I'd need an angle of 35 degrees extra from this point here. So I need to get to this point here as such. Okay? Now, again, if you had one of the 360-degree calculators, you don't need to worry about that issue. You can just go, I'm going up to 215. Here's 215 on that diagram. And again, same as I just done before, I'm going to use a nice line that connects up through that point, and then the point where my lines cross is exactly the point where P must be. And there we have it. We've measured our bearings, 110 degrees there, 215 there. Remember the key points about a bearing. A bearing is measured clockwise. In both cases, I've measured my angles clockwise from your north point. Measured clockwise from north. If you didn't do them clockwise, then you're going to end up with the wrong answer. Okay, next up. These triangles are similar. All lengths are given in centimeters. Work out the sizes of angles A and B. Okay, when you're dealing with similar triangles, they're deliberately done in this case to not look the same way around. So some people might automatically go, well, if I rotate this way, that 60 goes there and this angle goes there. That's not the case. You've got to be aware of where the similar sides lie. Okay, because this one or this one could have been rotated to look a different way. So this angle could be up here and this one here. It depends. So first of all, we can establish our scale factor. We can see that the hypotenuse as 10 has gone to 15. So 10 has gone to 15. Well, what do I need to do to get from 10 to 15? I've got to multiply all of these by the same multiple if they're similar. If they're similar, all of the things that get you from here to over here, the enlargements, have got to be multiplied by the same thing. Well, 10 to 15 I've times by 1.5. So in order for this to be a correct multiplication of correct enlargements, correct similar triangles, they have to be linked by 1.5. Well, look at the 8. 8 has also got to be multiplied by 1.5. But 8 times 1.5 is 12, not 9. The other side that we had here is 9, which means that this side, 8, links to C. C is going to be 12. The other one, where we're going from D, is going to be multiplied by 1.5, and you'll get 9. Well, what number times by 1.5 gives you 9? It's 6. 6 times 1.5 is 9. You do that by doing 9 divided by 1.5 on your calculator. So now we know this length here links to this length, and this length links to that length. So this is what's going to tell you where your angles belong. Angle A, for example, is between the 9 and the 15, so it's between these two, which means on the other triangle, it should be between the 6 and the 10, the sides that we took to get to there. So between 9 and 15, I had A. So therefore, looking between 10 and D, or 6 really, so this, I've got 63, which means that A is 63 degrees. Now, once we know that A is 63 degrees, you can work out what B is just by doing angles in a triangle. The angles in a triangle adds up to 180. So B is 180, take away that 63, also take away the 90 degrees that you have there. If you do that, then you will end up with 27 degrees left over. Okay? So that's how we establish which way the angles go around. Be careful not to label them the wrong way. They've deliberately moved these so that it looks like you're probably going to go for the upper one, the lower one. It's not how it works. Now, we've already done part B. Part B is to find the length C and D. I'm actually just going to move that onto the same page because there's no need for us to have a separate page for that. We know that C, as we've worked out, is 12. And D is equal to 6. Just making note that they are centimeters and centimeters. Okay? And we did that using the similar properties. Question 5. ABC is an isosceles triangle. D is the midpoint of BC. Explain why triangle ABD, so this one, is congruent to triangle ACD. So congruent triangles, remember, they are congruent if you can show that all sides are the same. Or if you can show side angle side, so they've got the same side, sorry, two sides are the same and one angle is the same, or angle angle side. This one's probably easiest done by doing side side side, because you can easily show that all sides are the same. So step by step. First of all, one side I know definitely is the same is that AD is the same for both triangles, because AD is a common side. So my rationale for that is it's a common side there. Another side that I know that must be the same for both triangles is this one here, AB and AC. Well, how do I know that AB and AC are the same? I know they are the same because they are the two equal sides of an isosceles triangle. So in brackets, I'll write down isosceles. Now, the other side, BD and DC, how do I know they're the same? I know they're the same because D is the midpoint of that line. Now, with all of that information that I've got there, AD, and then these two sets being the same, these two sets being the same, I know I've got congruent triangles by using side, side, side. And you must state side, side, side. Now, if you did it another way, let's say, for example, you established that you know the line that goes through an isosceles triangle meets the base at right angles. These two lines are perpendicular. Let's say you knew that. You could say, well, I know this angle here. With any two of them, you could do side, angle, side. If you wanted to do angle, angle, side, then you could use that right angle one and also say that you know that an isosceles line would bisect here. Or you could say that you know that this angle and this angle are the same because they're the base angles of an isosceles triangle. Any combination of them. The only thing you cannot do is say that all the angles are the same. Because remember that to say all the angles are the same doesn't give you congruence, that gives you similarity. So it's a different thing. Next up, a rescue helicopter sets out from a hospital on a bearing of 153 degrees. So drawing my diagram, here's my north line, 150 degrees. It's going to be about there. Okay, ooh, 153. Okay, 150 degrees to attend an emergency. The emergency could be down here. The pilot calculates that he needs to fly on a bearing of 327 degrees to return to the hospital. Is he correct? Well, for that, we're going to need to work out our back bearings. So we need to work out the bearing that's going to take us back from our emergency back to the hospital. That's this bearing here. First of all, I can work out this angle in the middle. This is the back bearing. So here, that angle is going to be, if you look closely, you've got two parallel lines. And we know that when we've got two parallel lines and a line going through, the angles between, like so, the C shape, they are co-interior angles. And co-interior angles add up to 180. So this angle plus this angle is 180 degrees. If I do 180, take away 153, that's going to leave you with 27. So this angle here is 27 degrees. And then, thinking about the bearing that I actually want to travel from the incident back to the beginning, well, you can see that's angles around a point. So we need to do 360, take away our 27. Now, there is a shortcut that you might be able to do just by basically adding these up. So adding those two, but we're not going to do that. We're going to do it this way. So 360 take away 227, and you're left with 333 degrees. So your bearing is 333, not 327. So no, the pilot is wrong. And you should state that the bearing should be 333 degrees. Okay? Next up, Omar is walking to the Burj Khalifa, which he knows to be 828 meters tall. He notices that at the top of the tower, it lines up with the top of a 3-meter post, which is 5 meters horizontally away from where he is. Omar uses the diagram below to calculate he still has more than 1 kilometer to walk. Is he correct? Well, what Omar has done is he has created two similar triangles. This similar triangle here, from where he's standing to the post that is 3 meters high, and from where he's standing to the tower, which is 828 meters high. And we know that these are similar triangles because this angle is common to both. This is a right angle and this is a right angle. And because these are parallel sides, these two angles here are corresponding. Remember the F-shaped angles between two parallel lines. So they are similar triangles. So what we need to do is establish the scale factor. you can see that this is 3 meters and it's gone up to 828 meters. Well, to go from 3 to 828, what you could do is just divide on your calculator. 828 divided by 3 is 276. So it's multiplied by 276 to get this length to here. Now that means that the 5 has also got to have the same process. To get the length from here over to here, you're going to have to do 5 times by 276. And if you do 5 times 276 on your calculator, you'll get 1,380. So remember that these are all in meters because we've not changed the units. So if that distance from here to here is 1,380, that means he's got to walk 1.38 kilometers just by dividing by 1,000. That is indeed greater, so more than 1 kilometer that he's got to walk. So yes, he is correct. And we can see it from that logic there. Okay. Last question. Zara claims that triangles ABC, so let's work this one here, and ADE are similar. Explain why she is correct. So as I said earlier, to prove two triangles are similar, you've got to show that the angles are all the same. The angles are all the same through certain properties. First of all, of these two triangles, the big one that encompasses the whole thing and the little one that just includes this bit, you can see they've got a common angle of A. Okay, at A, sorry. So the angle BAC is equal to the angle DAE. Just think you could have added it in logic of the two triangles, BAC, DAE, and that's because it's a common angle. In addition to that, looking at these two angles here, these are two angles that should be the same, and we know they're the same because they, if I two parallel lines which I've got here and here, BC and DE, that's a set of corresponding angles. So the angles ABC and BDE, or ADE even, to use the logic of the triangles, they are the same because they're corresponding. By the same logic, I can also establish that the angle ACB, this one, and AED is also the same because they're also corresponding. So ACB is equal to AED. So they're therefore corresponding. So I therefore have now proven this. All angles are the same. So therefore, similar. The triangle is similar because all of the angles are the same size and in the same position. But for a triangle, it doesn't really make a difference. If all angles are the same, it doesn't matter. You can change the orientation to get the right order. And there we have it. Okay, that's this test out the way. I hope this was okay. If there are any questions, let me or your teachers know. Take care, everyone. Bye.